everyone, and thanks for joining us today. My name is Priya, and I'm the marketing lead here at VTEX. A couple of reminders before we get started. The recording of this webinar will be up on our website by the end of the week, and I'll be sending an email out with the link to everyone here. If you have any questions, you can type them in the Q&A box or in the chat box. So today's presentation on breaking down breakouts is presented by Rich Whitty, sales manager here. Rich graduated from West Point in 1987. After serving in the Army, he embarked on a career selling capital equipment to the semiconductor industry, specifically iron beam milling equipment and iron implanters. Rich has many years of experience and joined VTEX earlier this year. Now over to Rich.
Thanks, Priya. Just making sure that you can see my presentation on the screen?
Yes.
Okay. Thanks for joining us. Today we'll talk about going from 100 gig, migrating to 100 gig core, and being able to roll up your 100 gig switches, and how we're going to do that through Breakout. To sum it up, we're going to go from 400 gig core migration in data centers with your legacy switches. We're going to talk about this, but basically we're going to use a QSFP, double density, different types of flavors. We're going to concentrate on one flavor, which is the DR4, which has a key advantage. It can interoperate with single Lambda optics. And that would be of the 100G variety. The 100G DR1 is going to be what we're going to have as compatible with the DR4 400G migration. Okay, so the first thing we're going to do is we're going to look at form factors, specifically for 400 gig. We're going to take a look at the different types of modulations. Specifically for 400 gig, it'll be PAM4, but we also want to look at non-return to zero modulations because it has to be backward compatible with 100 gig. And of course, most of the 100 gig is NRZ modulation. Then we're going to look at transceiver types and interfaces for the 400 gig. And then we're going to look for compatibility with the 100 gig. We're going to look at the old products, which are the MUX QSFP28, where you take basically four 28 gig signals and mux them together and send them down a single wire, versus the single Lambda architecture, which is going to be used to interface with the 400 gig. So let's take a look at some 400 gig form factors. The first thing we have are the CFP8s, and then we have the QSFP56 double densities and the OSFPs. The OSFPs they're a little bit higher power requirement and a different thermal budget management. So while they're out there, they really haven't risen to the top or come to the forefront to be used in breakouts. The QSFP double density really has come to the forefront. It uses lower power, and it also has a thermal management system that's compatible with the 100G servers and or switches. I'd like to also talk about modulation. In the QSFP28 100 gig transceivers, you basically had non-return to zero, or NRZ. It's got two states, a 1 and a 0, and it's fairly straightforward. In the 400 gig, everybody's moved over to PAM4 modulation. You can see there's 4 levels or 4 steps, and you have 1/3 of the amplitude, which translates into twice the data density and 4 times the data rate. So instead of a 1 or a 0, you can have 1, 1, 0, 1, 1, 0, and 0, 0. One of the issues that comes up with moving over to this modulation scheme is that you have lower signal to noise ratio. So it's a little bit more difficult in the terms of being able to transmit this data, and it's going to require digital signal processing chips, or DSPs, within the CDR, or the clock data rate. We can also take a look at this on the left. You can see there's a very poor PAM4 modulation. We call the little areas in between the lines the eye, and you can see this is a very poor open eye scheme. And you can see on the right a little bit better modulation, better signal noise. And we do need, when we moved over to PAM4, we do need a more robust forward error correction than we did on NRZ. And this new forward error correction is called KP4 FEC, or forward error correction. This FEC actually resides inside the DSP CDR chipset, which we could also call a retimer, which is just a chipset that's actually resides within the pluggable itself. Let's talk a little bit about the 400G transceivers that are available today on the market. We have our SR8s, our DR4s, our XDR4s, also known as DR4+, our FR4s, and our LR4s. In development, we have PLR4, SR4.2, which is a BiDi scheme, or bidirectional, FR8s, LR8s, and ZR, which are using coherent optics. We won't really get into those too much, but let's go back and talk about the ones that are readily available on the market today. The SR8 is good up to 100 meter reach, and it's multi-mode, and it's used as an MPO16 connector. On the electrical side, on all of these, we're talking about 8 by 50 gigabaud, and on the optical side, we're talking PAM4 modulation. We're talking 8 by 50 for the SR8s in a parallel mode. And then when we go down to DR4, which is a 500 millimeter reach, we go to single mode fiber and an MPO12 connector. Once again, everything is PAM4 8 by 50 gig on the electrical side. On the optical side, under DR4, now we're getting into a parallel mode where we have 4 100 gig signals that are sent, which is going to be advantageous for our breakouts. The XDR4 is kind of like an FR4 because it still goes 2 kilometers. But the difference is that we can use a different connector, an MPO12, and it kind of mimics the same thing as the electrical side is still 8 by 50, but the optical side now is going to be 4 by 100 sent in a parallel mode instead of muxing or multiplexing the signal. When you get it down into FR4, which is the standard 2 kilometer reach, you're going to find that it's CWDM, or coarse wave dispersive multiplexing. That's where we're going to go ahead and take 4 signals, and we're going to mux them into 1 signal and send it down the line, which is not going to be compatible with breakout applications. The same with the LR4, which is a 10 kilometer reach, still single mode fiber, but we're taking a coarse wave dispersive multiplexing, taking 4 signals, muxing them into 1 signal and sending them down a line, and then demuxing them on the other end of the line, just like the FR4, which once again will not be compatible with our breakout applications. One thing I'd like to note is we do have in development a PLR4, which is 10 kilometers, which will basically be taking the signal and putting into a parallel mode. So one of the things that I've marked out in red, the transceivers that are compatible with breakout on the 400 gig side are, and you'll see this, 95% of everything right now is going to be DR4. And then you've got the XDR4, which is really just another name for the for the FR4, Frank Romeo 4, except the XDR4 is in parallel mode instead of CWDM. And then the PLR4, which is basically the LR4 in parallel mode instead of CWDM. These all have MPO12 connectors, so you can see the commonality for the breakout compatible cables are going to be single mode. You're going to have an MPO12 connector, and the optics are all going to be parallel 4x100 gig optical signals. Here's just a little bit of the PAM4 CDR solution. You can see it uses a DSP on the gearbox, and we're going to take 8 electrical signals in and transform them into 4 100 gig signals. And on the right here, you can see the wires that are coming out, and of course 4 on the top are for transmit and 4 on the bottom are for receive, but you can see they're all in parallel mode. So what we're going to do is we're going to use this in a breakout consideration. We're going to use an MPO12 connector to plug it in, and we're going to be able to take those parallel optical signals and we're going to send them out to 4 individual single Lambda 100 gig transceivers. So once again, what we're going to need for compatibility on the 4 to 100 breakouts, we need a PAM4 modulation scheme on the optical side. We need a robust FEC, which is FEC KP4 for forward error correction. And once again, this FEC actually resides on the transceivers, not on the host side or inside the box. One thing that we'll talk about is we've got 2 right now which are available for breakouts, is the 500 meter and the 2 kilometer reach. And we do have a 10 kilometer in development for future applications. Now let's talk about the single Lambda 100G transceivers. These are fairly new on the market, and they have a more robust forward error correction, which are going to be able to talk to or interact with the 400 gig transceivers, the QSFP-DD transceivers. Once we have the FEC that's located on the transceivers on the breakout applications, the FEC is going to be turned on the transceivers, but you're going to turn FEC off on the host or inside the box. That's one of the things that people forget, that they leave the host FEC on and it doesn't interoperate with the breakout transactions. One thing that's new on the 100 gig transceivers is that they have to use a retimer in the digital signal processing gearbox in order to go from 100 gig optical to 4x25 gig NRZ electrical. And remember, the optical is PAM4, and they're going to transmit that into NRZ on the electrical side. So there's a retimer in the gearbox to allow us to do that. So this is the legacy 100 gig. You can see that you've got 4 laser diodes, and these laser diodes are being muxed into one signal, and the signal's coming down the lane. And then, of course, on the other side, you'd have transmit on one side and receive on the other. And then at the end of the line, it would demux and separate into 4 separate signals. This is NRZ signaling. It's not PAM4. And this is the QSFP28 that we're all familiar for the 100 gig before the single Lambdas came out. Well, let's talk a little bit about the difference between this and the single Lambdas, the newer models of the 100 gig that are used for breakouts. So the single Lambda is still 25 gig NRZ on the electrical side. Now what we're going to do is we have a digital signal processor with a CDR and retimer. It goes into one EML, electrically modulated laser, and that laser sends out one signal on a single wavelength, at 106 gig or thereabouts. And then on the receiver side, it goes into a pin diode receiver and an amplifier back into a DSP with CDR box, which changed it over to 100 gig on the 100 gig NRZ on the electrical side. But we can see on the optical side, it's now all PAM4, not NRZ. And so if you can imagine, each one of these 100 gig transceivers are going to plug into one of the 4 parallel lanes of the 400 gig transceiver, which is also PAM4. So we have a PAM4 commonality on the on the optical side, as well as a robust KP4 FEC, which are going to let them interoperate together in a breakout application. So let's take a look at that visually. So you're going to have, in this case, a DR4 transceiver for 400 gig. Also can be used with an XDR4 transceiver, which is really 4 FR4 signals. It's going to go down a 4-pair parallel single mode fibers, and we're going to be able to break that out into 4 separate single lambda 100 gig transceivers on the other end. The cable itself will be an MPO12, and then it'll be 4 duplex LCs on the breakout side. These breakouts also come in active optical cabling as well, or AOCs. At this point in time, we're really talking about transceivers themselves with a separate interface for the cabling. So at this time, are there any questions?
Thanks, Rich. So while we're waiting for questions, can you expand a little more on the, like I understand you can use AOCs or DACs also as breakout. Can you
Sure.
expand on that?
Sure. Inside, when you talk about the servers inside the core, when you go from a server to a top of rack, you probably are going to want to use DACs, which are direct attached copper. And you just go from electrical to electrical. There's really no need to change the signal over to optics. At a certain point, you're going to find out that the wire diameter is going to increase to the point where they're no longer really flexible. And so at about above 2 meters, you're going to go from a DAC to possibly an AOC, which is good for probably top of rack to end of row. Anything beyond that, when you're going to go from the end of row to possibly the leaf inside a data center, you're probably going to want to go with, that'll be like 500 meters. So you're going to want to go with the transceivers themselves, and then the breakout cabling separate. There are other options when you go from, when you're going longer than 500 meters. Once again, you could use the XDR4 to the XDR1s, which will go longer to 2 kilometers. So that'll go, from the spine outwards. And at some point in time in the future, we may even have the LRs to go 4 kilometers to do breakouts when you're going to the, to the edge or wherever you're going to have your access capabilities.
Okay. And I'm sure there's a cost point to that as well.
Yes.
And
it's all about migrating to, migrating a 400 gig within the core and when you're going to roll that out, interoperability with legacy 100 gig switches.
Sure. If you have any questions, you can type them in the Q&A box. Just a reminder. So here's a question. Where do you see the OSFP form factor?
So OSFP is around. We actually see that more on the 800 gig applications. I think the thermal management, really kind of threw that out of the equation because it really wasn't interoperable with the legacy systems. So we're seeing that the QSFP double data rate, double density is a little bit better for legacy systems, but we are seeing that the OSFP, which is a little larger, has thermal management considerations, which are probably looked at a little bit more within the 800 gig products that are coming out right now.
Okay. Another question. What advantages does a PAM4 modulation give?
You can put more data down the pipe. Instead of having, let me see if I can go back. You can see that there's additional steps. Instead of having a 1 or a 0, you've got 0, 0, 1, 0, 0, 1, and 1, 1. So now you have four different levels of data that you can send instead of 2. Instead of just a discrete on or off, now you've got multiple signals you can send down the same data pipe. So it's allowing you twice the density and up to 4 times the rate. And once again, if you look at the 100 gig offerings that prior to the single Lambda, they were all NRZ. In order to go to 400, a new modulation scheme was needed. So they went to PAM4 to increase the data rate. So you went from 100 Gs to 400 Gs. So you increase the data rate by 4 times by this new modulation scheme. And once again, some of the trade-offs were that you've got an inherently noisier signal. So you basically lower signal to noise makes you use FEC or forward error correction, and it has to be a more robust flavor of error correction.
Okay. Thanks, Rich.
Thank you.
So if you have any more questions, just you can email us info@btextech.com. So once again, I want to thank everyone for joining us. Someone has asked about the slides from the presentation. So I will be sending an email link to this webinar. And if you want any slides, if you want the slides or the PDFs, please send an email again to info and I'll send you the slides. So thanks again and have a wonderful rest of the week.
Thank you very much.